Hello everyone. Today we will introduce some basic knowledge of Carter generators. In terms of content, we will divide it into 4 parts. The first part is the composition of the generator. That is, what components does a generator consist of? In the second part, we will talk about the coil winding method. Different ways of winding the coils will have a great impact on the performance of the generator. We will talk about what is a loose winding coil, what is a mold wound coil. In the third part, we will introduce the excitation system. Different excitation methods. The generator also shows different characteristics. Last part is the Automatic Voltage Regulator, AVR. Is the voltage of a generator stable? It is an important performance indicator of the generator. The stable voltage of the generator is controlled by this automatic voltage regulator. First, let's talk about the 2 keywords about the Carter generator. One is brushless, and the other is brushless. One is synchronization. We know that the earliest generators had carbon brushes. The function of the carbon brush is to supply DC power to the rotor, allowing the rotor to generate a rotating magnetic field, and then generate voltage on the stator. Later, people designed brushless generators. So how is it achieved? Brushless generators use the rotor of the excitation generator to generate electricity, and then use the rotating commutator for rectification. The parts mentioned above are all on the shaft of the generator and rotate together with the shaft of the generator, so that we can remove the carbon brush, which is a relatively easily damaged component. Another is the concept of synchronization. The so-called synchronization means that the speed of the rotating magnetic field of the generator's rotor is consistent with the speed of the rotor. In this way, we can know that the speed of the rotating magnetic field of the generator is consistent with the speed of the engine we drive it. So we can control the engine speed to achieve the purpose of controlling the generator frequency. From this point on, unless otherwise specified, the generators we refer to brushless synchronous generators. The relationship between the frequency of the synchronous generator and the engine speed is the relationship between the two. We can use such a formula to express it. In our actual application, the most common generators have 4-pole rotors. So we can simplify this formula and Gethy's bring the number of magnetic poles of the generator rotor, 4, into this formula. And you will get such a formula. The engine speed, which is equal to 30 times the frequency of the generator output voltage. Specifically, For our common 50 Hz generator, the rotational speed is 1500 rpm. This 1500 is equal to 30 times 50. So we know that there is a 30-fold relationship between the frequency of the generator and the rotational speed of the engine. From here we can know that the frequency of the generator is determined depends on the engine speed. And only depends on the engine speed. This is when we assume that the generator is a 4-pole generator. The picture below is a photo of a 4-pole rotor. We can see its top. There is a magnetic pole on the bottom, left and right. This is the composition of the so-called 4-pole rotor generator. On this page, we list all the parts that a generator may have. Let's see which ones are there. The first one, of course, is the main generator. The electricity generated by this main generator is what we need and is used by the load. Then, its rotor provides the magnetic field. The rotor has a magnetic field and the stator can generate electricity. The second one is the excitation generator. The excitation generator generates electricity from the rotor. After generating electricity, it provides excitation current to the rotor of the main generator. In order for the excitation generator to generate electricity, it is necessary to supply power to the stator of the exciter, so that it can provide, in the excitation generator. The third magnetic field is the rotating rectifier. This rotating commutator converts the AC power emitted by the rotor of the excitation generator into DC power and supplies it to the main rotor, excitation. The fourth one is the voltage regulator. Usually an automatic voltage regulator, AVR, is used, which means it does not require manual intervention. The English abbreviation is AVR. Then, it is the mechanical part of the generator, including the generator shaft, bearings, couplings, housing, etc. In addition, there will be a cooling fan near the coupling, which cools the windings. With the parts we have mentioned above, we can already form a generator. However, in order to improve the performance of the generator, you can also add some optional items. These items include, first, a space heater, which is used to dehumidify the windings of the generator, so that the insulation performance of the windings can be improved. Then, there are sensors for winding temperature and bearing temperature. These are the last two items used for generator protection. They are the first required by the excitation system, corresponding to the model, and the auxiliary coils. This auxiliary coil is a coil placed next to the stator of the main generator and specially used to power the AVR. We have another way to power the AVR, which is to use a permanent magnet generator. In this case, there are actually 3 generators on one generator, main generator. Excitation generator. Permanent magnet generator. This permanent magnet generator is a separate generator. Its rotor is a permanent magnet. Because it is a permanent magnet, there is no need for excitation current to provide excitation. It can have a magnetic field and then its stator generates electricity. After the stator generates electricity, it provides power to the AVR. After knowing the composition of the generator, let's take a look at the structure of the generator. The first is the main generator. This main generator consists of two parts, the stator and the rotor. Let's first look at the legend on the lower right. In this illustration, the blue color indicates that this part uses direct current, and the red color indicates that this part uses alternating current. Therefore, the rotor on the main generator needs direct current, and then its stator emits alternating current. Looking to the left, it is the excitation generator. The excitation generator is just the opposite of the main generator. Its stator requires direct current, excitation, and then its rotor emits alternating current. After the rotor emits alternating current, it is sent to the rotating commutator. After the rotating commutator rectifies it into DC, the wire is then sent to the main rotor of the generator along the shaft of the generator, thus providing excitation current to the main rotor. These are the two basic generators in a generator. There is another component in the lower left corner. What is this component? This is what we often call AVR. Automatic Voltage Regulator. So what we draw here is relatively simple. We only draw the two output lines, F1, F2. But how to provide its power supply? What other adjustment functions does it have? None of this is shown here. We will introduce it as a key point later. Here we will ask a question, that is, where does its power source come from? We will find that where the AVR gets its power source is a very important issue, because it will have a great impact on the performance of the generator. On this page, we will take a look at the structure of the Carter generator through real photos. Let's take a look first. The picture on the left. In this picture, the generator casing and the stator coil are cut open, so that we can easily see the inside of the generator. The white part is the cut surface of the stator coil. This part is the coil of the main rotor of the generator. This part is the fan of the generator. Here is the bearing. Then this is the shaft of the generator. Here we can see a little bit of it, which is the AVR of the generator, which is the automatic voltage regulator. Then let's look at the picture on the right. The top one is the copper bar that the generator outputs. Then here we see the bearing bracket at the end of the shaft. What we see is a permanent magnet generator. The stator of the permanent magnet generator has also been cut open. The middle part is the white part of the permanent magnet, which is the heatsink of the rotating commutator. Several commutators are installed on the heatsink. To understand the technical performance of a generator, we need to look at it from three aspects. This is the winding. The way of winding: is it a die-wound coil or a scattered coil? The second aspect is the excitation method. Excitation methods can be divided into three types: self-excited, internal excitation, and permanent magnet, external excitation. The third aspect is the automatic voltage regulator. Automatic voltage regulators are divided into analog and digital types. Here we also briefly review some basic concepts of alternating current. This is the maximum value and effective value of alternating current. Let's look at the picture below. Let's look at the green line first. The green line represents the waveform of the B-phase voltage of the generator. We can see that the voltage of the generator is constantly changing, periodically, over time. Therefore, its measurement method cannot be like that of direct current. How do we do it? What about measuring the voltage of alternating current? We first need to know its maximum value, which is the voltage corresponding to the highest point of this waveform, or the voltage corresponding to the lowest point. Then its absolute value is also the maximum. This is the maximum value of alternating current and then the effective value of alternating current. For example, when we use alternating current to heat a certain device, it is to convert electrical energy into thermal energy. At this time, we can calculate its effective value based on the heating effect produced by alternating current compared with direct current. In fact, what we usually talk about is the effective value of alternating current. There is a fixed relationship between the effective value and its maximum value. That is, the effective value is equal to the maximum value divided by square root 2. In order to have a more intuitive understanding of alternating current, we directly use an oscilloscope to measure the alternating current we usually use. This is the alternating current we measure in the office. Of course, it is only 220 volts. Power supply. You can see that this single-phase power supply has a waveform like this. It is basically close to an ideal sine wave AC load. And it is also very different from a DC load. Therefore, when we measure power, there are three concepts of power. One is active power. The so-called active power means that the effect it produces is equivalent to that of direct current. The equivalent part of the power is active power and then reactive power. The so-called reactive power means that it has current, but it is not converted into other forms of energy. It is just the current walking around there. This part of the current multiplied by the voltage is reactive power. The third power is apparent power. Apparent power is obtained by multiplying the total current by the voltage. At this time, we do not distinguish whether the current is an active current or a reactive current. It is a total current multiplied by the voltage, which is the apparent power triangle. In order to illustrate the relationship between power triangle is usually used to illustrate that the power triangle is a right-angled triangle. The two right-angled sides are active power and reactive power respectively. The hypotenuse can represent the apparent power. Here we also need to introduce the concept of power factor. The so-called power factor is the active power divided by the apparent power. The value of the power factor is equal to the cosine value of this angle in the power triangle. We generally abbreviate the power factor as PF. Its value is equal to cos phi, which is a unitless. There are three measurements of power, each with its own unit. Usually, we can tell what power it is based on the unit. The unit of apparent power is kilovolt amperes. The unit of active power is kilowatts. And the unit of reactive power is kilowatts. The English abbreviation is kvar. Modular wound coils and random winding coil. Let's first take a look at what is a scattered coil. The picture on the right is a stator with scattered coils. This photo was taken when it was still a semi-finished product. We can see that the coils of the stator have been wound up. If we look at the local cross-section of the stator coil, it will be like this. For example, let's look at the set of coils below. This set of coils has a total of 4 turns, 4 turns. For example, the fourth green turn, we will find that it is composed of many small strands, which is what we usually see. This kind of enameled wire is composed of strands that are put together one by one. Between these small strands, you can see that they are squeezed together with other turns of coils, and they are arranged together in a relatively irregular manner. This form of coil is called a loose wound coil. This is a loose wound coil that is not placed in the stator slot. You can see that this turn of the coil is composed of many thin enameled wires. Then let's take a look at the mold wound coil. It is a semi-finished product of a mold wound coil. When we saw this photo, our first impression was that the coil was very neat and regular. In fact, each coil in it was pressed with a machine mold, so every turn of it has the same shape. So this is why it is called a mold wound coil. Then we look at the cut section of this coil. From the cut section, we find that the wires inside are not as we saw before. The enameled wire in the scattered winding coil, its cross-section is circular. The cross-section of the mold wound coil is a square or a rectangle. Of course, it is actually a rectangle with rounded corners. So in fact, the coil is made up of a corresponding cross-section. It is composed of large copper strips. Since the shape of the copper strips is very regular, the coil is very neat and tight when embedded in the trunking. Then, it can also be covered with many thick insulation layers. So this kind of generator insulation will be better. This is a mold wound coil that has not been embedded in the wire trough. Each turn of this mold wound coil is pressed with a mold. This is the coil we use. This cross-section is made up of square copper strips neatly stacked together, and then wrapped with an insulating layer. This insulating layer is usually tied up with mica tape-like tape. We know that mica is a materials with very good insulation properties. So this mold wound generator has better insulation and can withstand higher voltages. I just talked about what random wound coils and mold wound coils look like. Now let's compare these two coils. Let's summarize their performance. First of all, let's talk about the insulation performance of random wound coils. The insulation performance of random wound coils is worse than that of mold wound coils. The reason is that the shape of the coils is not very regular, so the insulation cannot be done perfectly. Then in terms of mechanical strength, since the scattered coils are arranged irregularly, the gaps in the middle may be uneven, so the coils are more likely to deform when subjected to force. Then there is the conductive performance. Since the scattered coils are made of this enameled wire is made of very thin wire, so generally speaking, its total cross-sectional area is slightly smaller, which affects the conductive performance of the coil. In contrast, the mold wound coil will perform in these three aspects. The performance is better than that of random winding coils. The first is that the insulation performance will be better, and the second is that the mechanical strength will be higher. Why? Because its shape is very regular. It is stacked together firmly with no gaps in the middle, and it will not deform when it is stressed. In fact, when our generator is working, the relationship between the rotor and the stator is there is a powerful interaction between them. As for the mold wound coil, it will not be affected by this interaction force and deform. The conductive performance is directly related to the cross-sectional area of the core. Since the cross-sectional area of this square copper strip is large, its conductive performance is also good. Generally speaking, the performance of mold wound coils is better than that of random wound coils. However, mold wound coils also have its disadvantages. That is, its price is high, or its cost is high. The random wound coils also have its advantages, which is its manufacturing. The cost will be lower, and the price will be lower. Then let's take a look at the application selection. What principles should be followed to choose whether it is a random winding coil or a mold wound coil? We will consider it from 4 aspects. First, the machine is a backup whether it is for main use or continuous use, that is, the type of application. If it is used continuously, it means that it will be used for a long time. We will tend to use mold wound coils, and then in terms of power, from small power to high power and small power. Consider using random coils. But for high power, mold wound coils must be used. The third aspect is the cleanliness of the environment, moisture and other factors. In a clean and dry environment, we can use loose wound coils. But if the environment is dirty and humid, you should choose a mold wound coil. The fourth aspect is the nature of the load. If the nonlinear load is small, we can consider using a loose wound coil. If there are many nonlinear loads, you must use mold wound coils. According to these 4 principles, we have made such a picture. What does this picture mean? If it is green, it means it is recommended and available by us. The yellow mark means that it may be used, but we need to pay attention. Red means that it cannot be used. In that case, there will be problems in using it. Finally, we will summarize it, which is to give us a more direct guide on what situations we can use this random winding coil when actually choosing this winding type. What about the next choice? The first is the low voltage generator, which is what we call a 400-volt generator. Then its rated power is relatively small, and its application is a backup type. The running time is not very long and the environment is clean and dry. In addition, there are no or very few nonlinear loads. When these conditions are met, we can choose scattered winding coils. In other cases, we must use mold wound coils. This is a high voltage generator. Carter's high voltage generators. From 3,3 kV to 10,5 kV are generators with relatively high rated power. They try to use mold wound coils. Main generators or continuous use generators mean that the running time is very long. For this generator, dirty environments such as humidity, salt spray, like at the seaside, on ships, chemicals, sand and dust, and some debris in the workshop may cause pollution. Environment. We try to use mold wound coils in these situations. In addition, in the case of high nonlinear loads. In short, when we choose the winding type of the generator, we should choose it according to the conditions mentioned on this page. Excitation system. Regarding the excitation system of the generator, let's first talk about its classification and the classification method. In fact, we classify the excitation system according to the source of the power source of the voltage regulator. Brushless synchronization. Generators have three types of excitation systems, which are self-excitation. The first is self-motivation, which is the simplest. Self-excited means that the power supply for the voltage regulator comes from the main generator itself. It does not have a separate power supply to supply this voltage regulator. The second is internal excitation. This internal excitation is Carter's term, and its abbreviation is IE. If Leroy Summer is talking about it, it's AREP. In short, these two are two different versions of the same excitation method. In the generator with internal excitation, the power supply of the voltage regulator comes from the auxiliary coil dedicated for excitation. As we have said before, this auxiliary coil is in the main next to the stator of the generator. It is an independent set of coils, and its voltage will not be affected by the output voltage of the main generator. The third type is a permanent magnet generator, which means there is a separate permanent magnet generator, which generates electricity and supplies it to the voltage regulator. In order to explain the excitation method clearly, we drew some pictures. Let's first look at the self-excitation method. The so-called self-excitation method, as I just said, is that the power supply of the automatic voltage regulator is directly the voltage from the main generator, is the same as the output voltage of this generator. So there will be an obvious disadvantage here. That is, if the generator suddenly adds a large load, the output voltage of the main generator will decrease at this time. Then this reduced voltage will also affect the work of the AVR. So the performance of this self-excitation method is relatively poor. In addition, it also has a disadvantage. That is, the voltage builds up slowly, because when our engine first starts to rotate, the voltage of the main generator stator should slowly rise and wait until it rises to supply power to the AVR. The AVR will then excite the exciter generator, which will then excite the main rotor. This will allow the voltage of the main generator to rise again. So after in this cycle, the voltage of the main generator is relatively slow to build up. Another disadvantage is the main rotor of our generator. In fact, when our generator establishes the voltage, it needs to rely on the residual magnetism in the main rotor. When talking about this residual magnetism, even after our generator stops, this magnetism will not disappear completely. When it starts next time, the voltage will be finally established by this residual magnetism. If the main rotor has no residual magnetism, the generator will output voltage, or it will not output the voltage we need. At this time, we need to magnetize the main rotor. This is equivalent to a repair process. Let's talk about some characteristics of self-excited generators. The first one is that its cost is relatively low, because its structure is relatively simple. From the picture just now, we can also see that it has relatively few parts, so the cost is relatively low. It is generally used for spare parts. Its disadvantage is that it has no short-circuit capability. The so-called short-circuit capability means that if the current output by our main generator is very large, it will drag down the voltage of the entire generator. The drop will be very severe, and even the voltage will no longer drop, can't rise. This situation means it has no short-circuit capability. Of course, this self-excited generator also has safety certification from the underwriter's laboratory, which is the UL 2200 certification for internal excitation, abbreviated as IE or AREP. Let's compare this picture with if you compare the self-excited type just now. You will find that the IE excitation method has an additional A part. This A means the auxiliary coil. The A coil is specially used to supply power to the AVR. The advantage of using such a separate power supply is that the power supply of the AVR will not be affected by the electronic output voltage of the main generator. Suppose we have a large load added to it. The voltage of the main generator drops a lot. But no matter how much it drops, it will not affect the voltage output of the auxiliary coil. This excitation method has the same disadvantage as the self-excitation method, which is that if the main rotor does not, the residual magnetism, loss of magnetism, also needs to be magnetized. Because the residual magnetism is needed to establish the voltage AREP. We will also introduce this performance of the generator. Generally speaking, it is actually the same as the performance of the permanent magnet generator. The similarity is that except that it cannot establish voltage when there is no residual magnetism. Other aspects are actually very similar. The first one is that it has short-circuit capability. That is, if the output current is 3 times the rated current, it can withstand 10 seconds. And the voltage will not drop to a very low level and cannot rise to the rated voltage. This is the so-called short-circuit capability. Because it has this short-circuit capability, it can drive a very large motor even when a very powerful motor is started. And the voltage recovery will be faster. The third is that the waveform of this voltage will be better. And the transient response will be faster. The fourth is that it will cause less interference to other devices. This is telephone interference. coefficient and radio interference coefficient. These two indicators will be relatively low. The fifth one is suitable for nonlinear loads. Of course, the amount of this nonlinear load cannot be very large. Another point is that a permanent magnet can be embedded. After the permanent magnet is embedded, the magnetization process is no longer needed. Compared with the permanent magnet generator, it has another advantage. That is, its cost is lower. Of course, this method has also passed the safety of the underwriters' laboratories. Certified. That is, the excitation method of the UL2200 certified permanent magnet generator. Let's take a look at this picture first. There is a big difference between this picture and the previous two. That is, it has the part on the right. The part on the right is a permanent magnet generator. Its rotor is a permanent magnet. That is, no matter how long it is left, whether it is running or not, its magnetic field will always exist. Therefore, the permanent magnet generator can generate electricity under any circumstances. If the permanent magnet generator generates electricity, it can power the AVR. The AVR can output excitation current to the excitation generator, and the excitation generator can output current to the generator. The main rotor of the permanent magnet generator is so there is no need to worry that the main rotor of the generator will be demagnetized and the voltage will not be established. This will not happen in Carter's products. The ratio of the permanent magnet generator is more of them. So here we spend more time talking about T voltage and current parameters of various places when this generator is running. We assume that it is a low voltage generator. The output voltage here is 400 volts. Then the permanent magnet generator outputs an AC voltage of about 80 volts. And its frequency is 200 Hz. This is assuming that our engine is a 1,500 RPM engine. So the frequency of the permanent magnet generator is 200 Hz. This AC power is sent to the AVR. When AC power is supplied, there will be a rectifier module inside the AVR, converting it to DC for use by the AVR. Then the output of the AVR is output to the stator of the exciter generator. Generally speaking, under no load conditions, the voltage of the excitation may be 10 volts. About 1 or 2 amps. If the generator reaches the rated power output, the excitation voltage may rise to 3 to 50 volts, and the current will be 3 to 4 amps. Then we have to say let's take a look at the part that is included in these three pictures. This is the so-called external setting value. In fact, this external setting may be a knob on the control panel. The output voltage of the generator is adjusted through that knob. If we are running parallel machines. Next, when several machines are connected in parallel or one machine is connected in parallel with the mains, The voltage must be controlled by the parallel cabinet. The parallel cabinet controls the AVR through this input point, and ultimately controls the output voltage of the main generator. For this purpose, let's take a look at some characteristics of the permanent magnet generator. It is mainly used for main power supply or continuous applications. In short, it is the kind of application that runs for a long time. So it is suitable to use a permanent magnet generator. And then permanently the magneto provides an independent power source for the voltage regulator. This type of excitation method is very suitable for nonlinear loads. It has a strong short circuit capability and can withstand 3 times the rated current for 10 seconds without voltage collapse. The starting performance of the motor is also very good. The voltage recovery is very fast. The voltage waveform is good, closer to the ideal sine wave. The transient response is also fast, and it has less interference with other equipment. That is, its telephone interference coefficient and radio interference coefficient are relatively small. Of course, it has also obtained the UL 2200 certification from the underwriters' laboratories. Let us summarize here. The type of load is that if there is a nonlinear load in the load. In our when choosing the excitation method, what should we consider? Here we have a table. There are 3 excitation methods. We divide the load into 3 situations. One is all linear loads. The second is a nonlinear load of 40% or less. And the third is the 3 types are nonlinear loads of more than 40%. If it is a linear load, it is easy to say. That is, no matter what kind of excitation method is okay. If it is the second case, the self-excitation method is not optional, because the generator may not be able to control the output voltage of the generator in this case. In this case we can only choose internal excitation or permanent magnet. In the third case, when our nonlinear load is higher next, then we only have permanent magnets, which is the only option. At this point, we want to introduce this nonlinear load. The so-called nonlinear load means that when we add a certain voltage to the load, its current is not proportional to the voltage. Such a relationship is not a proportional relationship. But usually nonlinear loads are nonlinear loads. Common nonlinear loads include UPS, rectifiers, and frequency converters, which contain components such as thyristors. Speed, and so on. They are all nonlinear load excitation methods and short circuit capabilities. In fact, we have already said it before. Here we just organize it into a table to let us see more clearly. The measure of short circuit capability is 3 times the short circuit current. 10 seconds. Let's look at the standard self-excited generator. It cannot meet this standard. Then the internally excited and permanent magnet generators have automatic voltage regulators AVR that can withstand 3 times the short circuit current for 10 seconds. Some dialects may say that it is a voltage stabilizer. In fact, this is also true. Now let's look at the function of the AVR. The function of the AVR is to control the output voltage of the main generator to be equal to the set voltage. The set voltage may be we use a potentiometer to set it. Or it may be a voltage specified by the cabinet to output. The first one is the power supply. Because the AVR works, it requires a power supply. As we have just said, the power source of the AVR has 3 ways, which are divided into 3 excitation modes. Then, there is the input of the voltage setting signal, which comes from the control panel or the parallel cabinet. 3. It requires voltage sensing input. That is, the output voltage of the main generator must be fed back to the AVR, so that the AVR can control the output voltage of the generator. The last one is the excitation current, output by the AVR. And the AVR passes this excitation current. There are 2 classification methods for AVR to control the output voltage of the main generator. The first one is based on the induction input classification. This can be divided into 2 types, one is single-phase induction, and the other is 3-phase induction. The performance of the induction will be better than that of single-phase induction. Another classification method is the control technology used by this AVR. Is it analog electronic technology or digital electronic technology? The so-called digital electronic technology is it is said that our AVR has a CPU, which has computing power. The processing inside it is to digitize the analog quantities first and then process them. Let's take a look at some photos of the AVR to have an intuitive understanding of the AVR. First, let's take a look at a very old Carter's VR3 that was used 20 years ago. In fact, this type of AVR has been used for a long time. It is an analog automatic voltage regulator. This page shows some of the ones that are still in use today. One type of automatic voltage regulator is VR6, which is also an analog automatic voltage regulator. Another type is R448. R448 is an analog automatic voltage regulator used by Leroy Summer generators. The third type is called CDVR. CDVR refers to Carter Digital Voltage Regulator. From my experience, this CDVR feels the best, especially in the case of parallel operation. For example, if we have several machines in parallel or one machine needs in the case of connecting to the mains power grid. If we use an analog automatic voltage regulator, our debugging work may be more difficult. But using this digital voltage regulator, it will be very simple and the operation will be smooth, very stable. Let's compare the analog AVR and the digital AVR through a table. First of all, in terms of this working mode, the AVR may have three working modes. One is the automatic voltage adjustment mode, which is the voltage regulator. There is also a reactive power adjustment mode. This is when it is connected to the mains grid. We can set a fixed reactive power or power factor adjustment mode. This is also when it is connected to the mains grid. Let the power factor of the generator be fixed at a certain value. These are the three possible adjustment modes of the AVR. Then the analog AVR can only have this automatic voltage adjustment mode, which is the voltage stabilization mode. If it is a CDVR, these three working modes can have several other control or protection functions. For example, soft start control. Soft start means that we let the voltage slowly build up, so that the process of voltage increase is completely controlled under our control. The analog method cannot be achieved at this time, but we can achieve soft start with the digital method. For example, we can let it rise to the rated voltage in 5 seconds. In addition, the analog AVR cannot do high voltage, low voltage protection, high frequency, low frequency protection, reactive power protection, and rotating commutator protection. Yes, but the digital ones can do it. And then have inductive voltage input. The analog ones will be divided into single-phase inductive input and three-phase inductive input. But if it is a CDVR, all of them are three-phase inductive input. It is this volt/Hertz characteristic. This so-called volt/Hertz characteristic means that our generator is driven by an engine. If the engine speed changes, then the hertz of the generator, that is, its frequency, will change. So when the frequency changes, how should the voltage change? This is the volt/Hertz characteristic of the AVR. If it is an analog AVR, it will have a straight line or two straight lines to choose from. But if it is a CDVR, it will have a real curve, which is divided into different frequencies. There are three other functions of segment control. One is the PID adjustment of transient response. We know that when it comes to automatic control, PID is the most common adjustment method. Line compensation and communication interfaces. These three analog AVRs do not have them. But CDVRs all have them. Like the PID in this CDVR. For adjustment, we directly connect to the computer and then enter the PID value and line voltage drop on the computer, which means that we need to directly ensure the voltage at the load end. For example, the line from the generator to the load is relatively long, because there is a certain voltage on the line drop. Then if we use CDVR, we can ensure that the voltage at the load fully meets the load requirements. Finally, the communication interface, CDVR. This voltage regulator has a 1939 interface and an RS-232 interface. This interface is what we use programming, having introduced some AVRs before. We also want to introduce another form of AVR. This is called IVR, Integrated Automatic Voltage Regulator. This IVR is integrated in the EMCP4 control panel. Let's see how it is composed. Our previous AVR was a module. It was a separate module and had nothing to do with the control panel. But this IVR separates its control function and its output current function, which means it controls the voltage. The function is integrated in the EMCP4 control panel. The control panel gives an excitation command and then outputs it to the excitation generator of the generator through the excitation module. The excitation module is just equivalent to an amplifier, or we say it is an actuator. The excitation module is together with the EMCP module. This part in the entire dotted box is the integrated voltage regulator. Since our EMCP4 is a digital module, so the performance of this IVR is very similar to the performance of the CDVR we mentioned earlier. One advantage of using IVR is that it can reduce some line connections. For example, the output voltage of our generator itself needs to be fed back to our generator set. When we used the AVR on the control panel in the past, we needed to send the voltage to both the control panel and the AVR itself. But after we use the IVR, we only need to send the voltage and current to the EMCP4 at once. This control panel is enough, and there is no need for a dedicated voltage feedback signal for IVR. We have introduced so much basic knowledge about Carter generators. Finally, we will summarize it. In fact, when we introduce these basic knowledge, the main purpose it is for the selection of our generator. That is, how we choose a suitable generator for users. So we will introduce it in three aspects. The first is about the winding of the generator. Our principle for selecting windings is such a small power reserve, and the load is not very critical. We choose this type of winding with random winding, which can reduce costs. If it is an application such as a data center, its equipment is very important, is very critical. And in oil fields or ships where the operating environment is relatively harsh, In these cases, we should choose mold wound coils. The second aspect is to choose the excitation method. The excitation method is selected according to the type of load. If the load does not contain high power motors, frequency converters, UPS, etc., we can choose the self-excitation method. In other cases, we must try to choose the excitation method of permanent magnet type or internal excitation. The third aspect is to choose the form of AVR. The form of AVR is mainly related to the way our generator is used. That is, if we only use it on a single machine, then we can choose an analog automatic voltage regulator. But if we want to use it in parallel, we should choose a digital automatic voltage regulator, because this will have a great impact on the parallel machine. It's big and convenient. We will introduce so much about the basic knowledge of Carter generator. If you have any questions, you are welcome to communicate.
Nice.